tons of them. All right, so this would be 2, 1, and we just start off with angles. Something simple. Sadly, people mess up horribly. Wow, that messed up already. All right, so how do we start angles? Well, it's best to define them as the measurement between two rays. The two rays have to have a common starting point, and it's not a distance or anything, it is just a measure of basically rotation. And I usually label my angles theta, Greek letter, gotta love it, theta. You might as well get used to Greek labels. Later in the book, these things become known as vectors. They're not rays, they have a terminal length. And you still can draw the same picture. So as long as you have two rays that have a common point, the measurement, the opening between them is the angle measurement. So I always try to think of it as like a second hand and a minute hand and how they separate as they rotate away from each other. The angle will get bigger. Couple important angles. If you have this angle, that's a right angle, also known as 90 degrees. This angle, if I put my common point of my rays there, this is called a straight angle. How many degrees? 180. If I rotate my angle all the way around until it becomes a right angle again, 270. So the opening is going to be 270 degrees. And then if I go all the way around and wrap it up so that my two rays are lying right on top of one another, the rotation would be 360 degrees, but that's the same thing as 0 degrees, since they land right on top of it.
Couldn't a 271 be misinterpreted as a 90 degree?
It could.
If you're measuring if you don't know which one to measure.
The weird thing here is, notice my angles I keep opening in this direction. So that would be positive. So if you go this direction, the angle becomes negative. So this is actually negative 90 degrees. So it depends on which direction you go. So clocks go negative because they tick in that direction. They go clockwise. So clockwise is the negative direction for us in angle measurement, and counterclockwise is positive. Anti.
That's what they got.
Counter. That is a long word. Counterclockwise. This will be our positive direction. And clockwise will be the negative direction. Just like a number line, except this is rotational direction, instead of going a certain distance away from the origin. All right. What if I have an angle, and I like putting them in coordinate systems. If you put it in a coordinate system, you're guaranteed that this is what's called your initial side. When you let your angle equal 0 degrees. So you choose, it's just chosen. I personally think the y-axis would have been a better choice for an angle, because then you could think of it as a compass as it rotates around. But positive x-axis has been chosen as 0. So if you rotate the angle open to a certain degree, then where it stops is called the terminal side. So it terminates at that angle. And the measure between them, of course, is theta. Now, how far can I spin that terminal side?
As far as or until it goes all the way to its initial side.
So it only can do one rotation.
It can do multiple ones.
It can do multiple ones. Kind of like a tire. It's just going to go round and around and around.
But we don't know how many times it goes around.
Well, if we count it, we could. So if we have an angle of 560 degrees, that's more than 360, which is a full turn. How would I graph it? Well, it's going to go in the positive direction, so it's going to go around once, That would be 360 degrees. So what do I do to find out what's left over? Well, subtract. How many is left over? So from where I stopped, I have to go another 200 degrees. So where do I go for 200? What quadrant will I eventually stop in? The third quadrant, right? Because if I stop here to get this calculation and I continue on, that's another 180, so that leaves me 20 more. So this right here is 20 degrees. And my angle would be facing that direction. And this would be my there we go, side. That would be my terminal side. Now, is there an easier way to get to that terminal side? Sure. I could go the short way, or the correct way, just go from here to here. Well, how many degrees would that blue arc be?
200 degrees.
That would be the 200 degrees. So 560 degrees is the same thing as 200 degrees. Or, if I go backwards,
Oh,
It was
160 degrees.
-160.
Yeah.
No. If this is 200, then the only thing left is 160, so this would be
Yeah.
negative 160. So this is also equal to negative 160 degrees. So this idea here, these are called coterminal angles. They're angles whose measures land right on top of the same terminal side. That's all it does. You always try to pick the easier of the two. You could use 200, it's less than 360. 160 is nice because it's less than 180. And depending on the situation, you might want to use 200 sometimes and negative 160 other times. So try to get used to coterminal angles. It makes life a little easier later on. All right, that's the easy part. The switching your brains around is the second part. Most of you are comfortable with degrees. The problem with degrees is it has a unit of measure and it messes up some of our calculations. Let's see, for instance, let's say I have a circle and it has a radius of 5 centimeters. And I take that radius and I cut a central angle of 50 degrees. And I want to know how long is this arc? Just that portion of the arc as I sweep through it from the blue line to the green line.
Partial circumference.
It's a partial circumference. Were you taught how to do this? In degrees?
We remember
Alright.
what it is.
Start off with the full circumference. What's the circumference of a circle?
312.
Formula. Each formula for a circle has a 2, a pi, and an r in it. One's pi r squared and the other one's 2 pi r. Which one gives you linear units?
That was
2 pi r. Because if you say pi r squared, it
That's
gives
the
you
area.
square units,
Yeah.
which is area. So this is 2 pi r. So how do I find a fraction of the circumference? Well, you literally multiply it by a fraction. What fraction of the circle did I sweep through? 50 out of 360.
Yeah.
You got 360. So the partial circumference is called S. S represents arc length. And it's going to equal badly 50 degrees out of 360 degrees times 2 pi r, but in this case r is 5. It's very messy. But one thing comes out of it nice. What happens to the degrees? They cancel. If they didn't cancel, we get something called degrees centimeters, and that just doesn't make any sense. But in some of these calculations, the degrees don't cancel, and if you leave them there, it literally becomes like degrees centimeters. So it gets kind of messy. All right, so this arc length of this thing is? I have no idea. That's when calculators come in handy. That's 10. That's 50 over 36. That's 50 over 18. That's 25 over 9.
I have 4.36.
Did you include the pi?
Yes.
Okay. 4.36 No, I don't want to keep going. You always have to have a unit, though. Centimeters. So the arc length of this thing is 4.36 centimeters. But that's a long process, getting the ratio of the degrees, then multiplying by 2 pi, and then the radius, and the calculator does all your work, but still, that's kind of long. There is a better formula. And that unit degrees doesn't get in our way anymore, which is kind of nice. So what happens is, start off in a circle again. It's basically the same setup. I'll start with the terminal side of the x-axis and just give it a radius of r. So what we're going to do here, wow, a little squeaky there. If we open this up an angle, it's going to sweep. I love when they sweep, but that was a weird sound. It's going to sweep an arc length here, little squeakies, of s. So what we do is we're going to set up a relationship between theta, r, and s. And we define the angle theta as the ratio of s over r. Okay. So as you open this up, once s becomes equal to r, theta would represent 1. If s equaled 2 times r, then theta would equal 2. And then so forth and so on. But again, this is just a portion of a circle, which is kind of cool. All right, so what if I went all the way around? Well, then you would get theta is equal to, if s is all the way around, it goes back to circumference, which is 2 pi r, divided by, well, r. What happens to the r's?
Cancel out.
So we get a theta is equal to
Pi.
2 pi. So a full rotation under this measurement system is measured exactly as 2 pi. It's not 2 pi degrees, it's not 2 pi anything, it's just 2 pi. It's what's considered a unitless measurement. Because if s was measured in centimeters and r is measured in centimeters, those 2 centimeters are going to,
Cancel.
and you're left with no units whatsoever, which is beautiful. So a full rotation is 2 pi. Full rotation. All right. What if I did a half rotation?
Half of 2 pi.
Half of 2 pi, which would be 1 pi. This would be a half rotation. Oh, I forgot to say. What's a full rotation in degrees?
360.
360 degrees. Half rotation?
180 degrees.
180 degrees. So when I say 2 pi as a measure of an angle, it's the same thing as 360. If I say pi, it's the same thing as 180. Let's cut it in half again.
1 over 2 pi is 90.
So pi over 2 is
90 degrees.
a quarter of a rotation, but it's also known as a quarter rotation. 1/4 of the circle gives you 90 degrees. If I take half of it again,
45 degrees.
pi over
4.
4. This would be ridiculously an 1/8 rotation, but we don't care about that. That's going to be 45 degrees. So starting off with 2 pi, I can just keep slicing it in half and come up with all these other measurements. All right.
We done cut it in half?
I can keep cutting in half, but the problem is half of pi over 4 is pi over 8, and we get
This
What?
becomes a logarithmic sweep.
logarithm.
Yeah.
Oh, if you plot them. I wonder
A
if
negative
that's-
logarithmic.
I'd
Because
have
it
to try
decreases drastically and then slowly.
I'd have to look at it. It depends on what pi over 8 is equal to specifically.
Pi rate is 222.5.
Pi over 8?
Yeah.
Well,
That's half- that's
degrees
half.
wide.
That's half of 45 degrees.
Oh, no, I'm saying pi as being 3.14.
Oh,
That's what I was thinking of.
okay.
All right, so there is some relationship between these, but I'd like to get a little bit more precise so I can find all possible angles. It should be a one-to-one correlation. So this thing over here, I haven't given it a name yet. We're going to call it a radian. So this is the strict definition of what is called a radian measure of an angle. But I don't like saying the word radian because it literally has no units. So we just call it a radian, but but it doesn't have a unit of radian, which is kind of confusing in a weird way. And it only has this relationship to go by so far. So what I need to do is to come up with a way of finding any degrees in terms of radian. And the one I usually choose is this one. Pi is equal to 180 degrees. And if you do a conversion fraction, if I have, say, 40 degrees, and I want to change it into radians, this is an equality, so pi over 180 degrees is equal to 1, or 180 divided by pi is also equal to 1. Just don't type it in your calculator because the answer will not come up as 1. The only reason that they're equal to 1 is because they are equal to each other. Otherwise, decimally, they don't make sense. So what you do is you make sure your degrees end up in the bottom and your radians end up in the top so that your degrees will cancel. So this as a radian, 40 degrees as a radian, would be 2 pi over 9. And I always try to keep the pi involved when I'm talking about radians. It's another indication that you're in radians rather than degrees. Now you can change this to a decimal. What's 2 pi divided by 9? Approximately.
0.698.
0.698. This is an approximation of the angle, but this is the exact angle. I'd rather you leave it as exact, but if you do approximate, go at least 3-4 decimal places. And don't let it get confusing because 0.698 is 69% of the radius you've traveled along the arc line. That's all it's talking about. All right, what if you had 200 degrees? What would that equal as a radian? Go ahead. Or you're doing it in your head. Oh my God. Stare at it.
Just 2 pi. 2 pi over 10. Or 2 pi, yeah. 2 pi over 10. Oh no.
Pi over 9?
What is it?
Is it pi over 9?
There is a pi over 9 involved, but there's a number also.
Is it 5 pi over 9?
That sounds. Why do you keep guessing?
Is it pi over 9?
It's 20 over 18 after you get rid of the zeros, right? What goes into 20 and 18? Common number, divisor. O, C, D. Lowest common divisor. 20 over 18, what's it reduced to?
10 over 9.
10 over 9. So this is 10 pi over 9. Wow. Fractions. It also works going the other direction. So if I give you something in terms of radians, let's say 2 pi over 3, and you're curious where this would be located and you're not really comfortable with radians, you can convert it into degrees. What would go in the bottom of our unit fraction, that 180 or pi? What do you think would go in the bottom? Over here I chose 180 at the bottom because I wanted to get rid of degrees. Pi is going to go in the bottom. Now it doesn't get rid of any radians, but I definitely need the degrees to end up in the top so it sticks around in my answer. So something degrees. What's going to go away first? The pi. What's going to go away next? Well, 3 goes into 180 how many times? 60. And 2 times 60 is 120 degrees. So this would be located in the second quadrant. As you rotate off the positive x-axis, this would be the second quadrant. Now, is there an easier way to find out where 2 pi over 3 is? Sure. You might as well get used to it. So I'm just going to put a little box over here. 2 pi over 3. The first thing you look at, well,
Isn't there like a chart, like in the book or something, that has like all these?
blah, blah, blah. I love charts. But drawing it,
Charts
it's,
are too easy.
charts you have to memorize. I'd rather you just know how to get to it. But yeah, there's a chart.
I was just asking.
There's the associated ones you have to memorize are pi over 4, pi over 2 pi, 2 pi, pi over 3, and pi over 6. Those are the ones you have to know what the degree measurements of those are. Memorize those. But all the rest,
So it's
figure
pi
out.
over 3 and
Pi over 3 is 60, pi over 6 is 30. It always goes opposite of what you think. All right, so if you have 2 pi over 3, the way I think about it is if you take pi, how many degrees is pi?
It's 180.
180, which is a straight angle. If I cut that into equal thirds, that means as I rotate, I'm going to cut the top into 3 pieces. So this angle here is pi over 3, this angle here is pi over 3, this angle here is pi over 3. So 2 pi over 3
So we get 120.
would just go through 2 of the pieces. So it's in the second quadrant. Does that kind of make sense?
Yes.
All right, so if it was 4 pi over 3, where would it be?
In the third
Because this would be 1, 2, 3, and you'd have to go 1 more. So if you, it's just a counting method. It makes life a little bit easier. What about 7 pi over 4? Where would that be located? Now the 4 on the bottom tells you what you have to cut the straight line into. You have to cut it into 4 equal pieces. So you go 4 on the top, 4 on the bottom,
It's going to be in the fourth quadrant.
and back off 1. So that would give you 7, because that would be 8, and you have to back off 1. So it would be 4 on the top, 4 on the bottom, and I usually just back off 1, so it would be right there. So that's why radians are a little bit nicer, because it's really quick to say where they are located. And you can draw pretty pictures with them
So
too.
it's 315 degrees.
Well, I don't know. Well, it's 45 times 7. Is that 315 degrees? I think it is.
Yeah, should be.
I think it is. I'm not a very good mental calculation type person. I'm very good with theoretical garbage, but not very good with the mental stuff. Calculations. Boring. Did that. You can look up all those. All right. So applications. Most people do not do well at these, and I don't know why, because the formulas are really tiny little baby formulas. First one, arc length. This is that S in the formula. So if we start off with theta, radian measure, is equal to the ratio of the arc length and the radius of a circle. What I want to do is have this answer in terms of S. So to solve this for S, all you have to do is multiply both sides by R. So you get S is equal to theta R. Now most people don't screw that part up. What they screw up is this. How does theta have to be measured? It cannot be in degrees because this is the definition of radians. So theta has to be written in radians. It has to be in radian measure. It cannot be in degrees because we're getting this formula from the radian definition. Right. So for example, a circle has a radius of, I don't know, 15 feet. So the way I like to think about this is there's a rope that's 15 feet long and a goat is attached to it, and it's stretched all the way out. And the goat starts moving through the arc, and you want to know how far has he walked. But as he walks, he's got to stay within 15 feet of that post in the ground. So here's the post in the ground. Here's the length of the cord, 15 feet.
So you use the row top.
And your goat is going to walk on a path for a certain measure of angle. So a circle has a radius of 15 feet, and the central angle measures 100 degrees. What is the arc length? What is S? All right, so the goat here is walk through 100 degrees of measurement. Obviously, my picture's not going to match 100 degrees because it's going to wrap around. So you just, label. So what we're looking for is the length of the dotted line. Right. So what should be your first step?
To set it up, or change the degrees to radians.
Change the degrees to radians, because once you start setting it up, you're going to throw 100 in here and mess things up. So 100 degrees times what?
Pi over 180.
Pi over 180, you want those degrees to go away, so they have to be opposite of each other. So what's that equal to?
1 pi over 80.
5 pi over 9.
Calculator people. Cancel a 0, it's 10 over 18, 2 goes into both of them, 5 over 9. So theta is equal to 5 pi over 9. And now you can go and jump into the formula. So S equals theta r. So S equals 5 pi over 9
Times 15.
times 15 feet. Now when you measure this, calculate this, this has no unit measurement, but 15 has feet. So when you shove it all together, the answer stays in feet. So what's 5 pi over 9 times 15 approximately?
26.179.
26.179, so 0.2. So the distance traveled is that distance. Now this next one's not in the book, but I like teaching it because it shows up in calculus. And if you don't see it here, when you see it in calculus, you're just going to get all confused. You're all going to calculus, right? This is pre-calculus. So
Sadly, yeah.
it's kind of like pre-algebra. You just kind of go into algebra. So for calculus purposes, sector area. Basically the area of a piece of pie. So if you have a pizza pie, as they say in New York, and the pizza pie is, cut out like that, depending on the size of the pizza, if it's a 16-inch, an 8-inch, 22-inch, they have all different sizes.
And you were they got big pies.
Oh, yeah. Very thin though, I never liked
Yeah.
New York style pizza. And let's say we cut an angle out of it. My parents always had a rule. If you cut the pizza or the cake or whatever it is, you always got last choice.
You mean last choice?
Well, if you had first choice, you'd cut the biggest one you could find and take it. So if you got the last choice, you would want to make sure they're exactly the same. Otherwise, you'd be shorted because everybody would take the biggest pieces before you. So there was a rule: if you cut it, you got the last one.
Oh.
Yeah, my parents were tricky that way.
Well, what if you cut like smaller ones and then you save the last one for a big slice? That would be yours, wouldn't it?
Whoever got to the
Whoever
pizza
got
first,
the
they would
first
take the
would get the
biggest
biggest
ones.
slice.
You'd be stuck with the small one.
Yeah.
Yeah. So you were there going measuring it and making sure they're all equal. All right, so if this is what I'm looking for is the area of this piece of pizza. So we're going to start with the area of the circle, which is area equals
Pi over squared.
pi r squared. And what we want is a fraction of the area. Now, theta we're going to assume is measured in radians. So if I want a fraction of the area of the sector, there's no fancy letter that is used for the area of a sector,
It's just a sector.
is going, area of the sector. Arc length has a nice letter S, but this one doesn't. Is a proportion of the circle according to theta. Well, how much of the circle is cut by the measurement of theta in terms of radians?
We have to figure that out.
Now before, remember we had the 50 degrees and you put it over 360. So this is theta radians over
360.
full rotation in radians. Looking back at the
2 pi.
notes. 2 pi. So you would go theta over 2 pi times pi r squared. The fraction of the circle that we're looking for the area of. All right, the cool thing here is what happens to the pi's? They cancel. So the formula for the area of a sector is just equal to, dang it, I just wrote pi. Theta r squared over 2. Theta r squared over 2. So this is just the area of a sector. So if I go back to this problem and I say, if this is a goat on a rope, I love saying that, goat on a rope, Pope on a rope, never mind. if it's a goat on a rope and it sweeps through, you've never heard of Pope on a rope?
Mm-mm.
Oh, that must have been from that.
I've always heard of
80s.
soap on a rope.
Soap on a rope, Pope on a rope. It was a joke in the 80s. It's a long time ago. So if this goat had this as an enclosure, and he could graze anywhere he wanted in here, how much field could he graze on? How much field can he graze on? How much grass can he actually chew up area-wise? So the same thing would happen. You would change your degrees into radians, and then you'd come over here and say, oh, the area that he could graze on would equal 5 pi over 9, the degree theta. The radius is 15 feet, and you would square that and divide by 2. Now, when you do feet and you square it, what measurement do you get?
Square feet.
Square feet, which is an area measurement automatically. So what is this equal to? It's ugly, whatever it is. Approximately, how much grass can you graze?
I would have 196.34 square feet.
196.34,
34.
so 3 square feet. And even if you write it this way, you still have to say square feet, not feet
Yeah.
squared. Feet squared doesn't really exist.
Sounds weird.
Alright, so that is arc length and area. Now it's much more interesting. What if, oops, clean the screen. What if we have a tire, a wheel, has a radius of, I don't know, r, doesn't really matter, and we start rolling this wheel across the ground. Or we can keep it still and just kind of keep the measurement going, one of the two.
So let's say we invented the wheel.
So let's say you invented the wheel and we rolled it a certain angle, central angle in the middle. So if it started here at R and I roll it in this direction, the wheel would move to the right. So if I roll it in this direction and I stop here, so I went through this angle theta and the wheel actually moved across the ground. Well, how far did it roll?
I was just about to say you're gonna ask a distance question.
Oh, heck yeah. So how far it rolls is the
It's
length
same as
of the
length
arc.
of the arc.
Yeah, it's the same as the length of the arc.
I thought it was going to be the.
Because now we can go-
inside.
We're heading towards, if you have a bicycle and you're pedaling at a certain
Yeah.
rate and you know the measurements of your gears, you can find out how fast you're going.
Really?
It's actually not that hard. So we can find this arc length. Right. Now, this is just how far it travels on the road. Now, if you're pedaling, what determines your speed is how fast you're pedaling, right? So how do you measure that rate?
Revolutions per minute.
Revolutions per minute or revolutions per second, one of the two.
Yeah.
What does a car measure in?
Revolution per minute.
Is it per minute? I thought it was per
It's
second.
RPM, yeah.
RPM, yeah, you're right. RPS would be so much better.
Whoa.
Wind it out. So what we want to do is convert this arc length to find out how far you're going as you have this RPM. So we have to do a relationship between revolutions per minute and how fast. Now both of these are kind of question marked in the sense, get this out of the way, that I need to describe them in a different way. So revolutions per minute is how fast something is spinning. So that's going to have a weird measurement because it's really hard to talk about it. So it's the rate of radians per time frame, but I'll just put down here per minute. It could be radians per hour, radians per second, whatever it's going to be. So there's a relationship between radians per minute and revolutions per minute. They're not. There's a direct connection between them, but they're not exactly equal. We're going to call this thing omega. It looks like a W, but it's actually the Greek letter omega. It's rounded on the bottom. All right, and as this thing revolves around, S is going to be moving either faster or slower. So the point on the surface is going to have its own velocity, how fast it's moving along the wheel according to the distance. So we're going to call that V for regular old velocity. Now velocity is things like meters per second, miles per hour, things like that. So it's going to be arc length per minute, if you want to think of it that way. We can also write this as R over radians over time, and this also could be represented as arc length, or length, distance, over time. So both of them are rates, omega and V. Okay. Now, just have weirder names. This one is called angular velocity. This one is just called linear velocity. How fast it's spinning and how fast one of the points on the edge is moving in a linear fashion. In other words, how fast are you going along the ground if this is a wheel? Yeah. So how do I change revolutions per minute into omega? I think I might be skipping one little piece. Hold on. Make sure I know what I'm talking about.
Greeks are so confusing.
That's too. What? Greeks?
Yeah.
Yeah, they do some weird stuff.
I don't know. I think I remember the words.
Let me write this a little bit better. Formula. So this would be omega equals theta over t. Omega equals theta over t. Okay. So if I have 20 RPM, what does it mean to be a revolution?
It's one full
Cycle, right?
cycle.
So if I need to change that into radians, it's doing 20 cycles per minute. Each cycle is worth how much? In radians. 2 pi, right? So to change this into theta, we're going to get theta is equal to 2 pi times RPM.
So it'd be 40 pi.
40 pi. Cool. So theta is equal to 2 pi times the 20. So theta would be 40 pi per minute. Got to get that rate back in there. It's
Ouch.
40 pi radians every single minute.
Ouch.
Okay. So that'll give me omega. From omega, velocity is equal to s over t. The problem with s is, being arc length, we'd have to go and calculate it using s equals theta r and then take that answer and plug it back in here. But if you look at this formula, it already has theta involved in it. So my suggestion is this. What's s equal to? I just said it. What's s equal to? You might have to look back in your notes because I ain't answering. I just said it too.
I R.
What is
I
it?
mean, theta R.
Theta times r?
Mhm.
Theta times r. So I can write this as theta times r over t. It's a direct relationship that I can take s and change it into theta r because we're on a circle. But if you look at this, here's theta over t,
Which was that?
which is omega. So this turns into omega r. So I can do velocity rather than s over t as just omega, if you find omega first, times the radius. So the only thing I'm missing here is the radius. Did I get the radius for this problem?
No, you did not.
Let's give it a tire radius. What's a good tire radius of a bike?
Of a the bike 22 inches.
Is it 22 inches all the way across, right?
22 inch diameter, so 11 inch
11 inch.
radius.
So if this was a tire on a bike, it would have an 11-inch radius. And we would say that this is equal to omega r. And omega was 40 pi per minute. I'm going to put it all in there. 40 pi per minute. And the radius of the tire was 11 inches. So when it's all said and done, what's 40 pi times 11?
It is 1,382.3.
1,382.3. What unit of measurement?
That's gonna be inches per minute.
Inches per, because of the fraction, minute. What the heck does that mean?
That's how far you go.
Yeah, but can you visualize how fast you're going? Is that faster than someone running? Is it faster than a car doing
We
20
had to
miles per
reduce it.
hour?
We had to reduce it down to miles per hour.
Well, change it.
Yeah.
Change its units. Do you know how to change its units? Just curious.
You
Can you go from inches per minute to miles per hour?
can.
Okay.
It's not multiply, you divide.
Well, it's a lot of multiplication and division.
Yeah.
The way I usually do it is a fraction, a lot of them. So you start off with 1382.3 inches per minute. What measurement do you want to get rid of first? Inches or minute? It doesn't matter.
Inches.
Inches. So if I get rid of inches, I have to put inches in the bottom. What do you want to change it to?
Miles.
Do you know how many inches are in a mile?
Yes, you do.
Feet.
Remember?
I would change it into feet. All right. So how many inches are in a foot? That one you should know.
12.
12. So you put 12 down here, one up there. While we're working on the inches, what do you want to change feet into? Do you know how many feet are in a mile?
Yes.
5,280.
That's good. So I'll put feet in the bottom and miles in the top, and it's 5,280 for every single
inches are
mile.
in a mile.
Good lord.
63,360.
Good lord. That's too much. All right. So what is this equal to? Well, it's 1382.3 divided by 12 divided by 5280. So the inches go away, the feet go away, and you're left with miles per minute. It's going to be a very small number because miles per minute is kind of small. But just in case you're curious, you can do this. But leave the answer in your calculator. What is it anyways? Like 0.00?
0.021.
0.021?
Yeah.
But leave the answer in your calculator because I'd rather you keep all the decimals
I
for
was
this.
gonna say, then we need to convert it to hours.
Yeah, we got to change minutes into hours. So your answer, which was, what was it? Miles?
Yeah, when it's
Miles per minute. All right, now I got to get rid of minutes. So minutes go in the top,
Now we get this for hours.
hours go in the bottom, so it'd be 60 over 1.
So 2 times 60.
So that's all I want, right? Yeah, miles per hour. So it's whatever answer's in your calculator times 60.
1.3.
That's it?
Yeah.
Wow.
Miles per hour. In other words,
You're pedaling pretty slow.
pedaling very slow. 20 revolutions per minute. That's one revolution every...
That actually is fairly slow.
That's really
It
slow.
is very slow.
If you think about it.
20 revolutions per minute. Divide by 60, that's 1/3 of a revolution every single minute.
You're so cold hard.
It's very slow. Okay, so that is angular and linear velocity. So I'm going to give you a problem and see how you do.
Now, would that be the same as the same kind of way to find gear ratios in between two different gears?
Gear ratios is what I end with this usually.
Yeah.
But it's actually not hard because it's just the distance, the radiuses, and the tires, how big your tires are. We'll tell you how fast you're going.
You're talking about, yeah.
But gear ratios, yeah, you can do a comparison between their radiuses, and if you get a cheap bike, many of them give you the same ratios.
Yeah.
And if you get an expensive bike, none of them match each other.
Oh.
Yeah, they're,
And then you've got different gears that you can change in between.
yeah, but you could be on the big upper gear, the third gear on the front wheel, and maybe the third gear on the back wheel. It's the same as the first gear on the back wheel and the second gear on the big wheel. So that just constitutes a cheap bike. because they don't have as many gears as they advertise. All right.